Hey, Mr. Smith here. Welcome back. I'm super excited to share this deck with you. The period of the late 1800s is one of the most all-time interesting areas if you care about the history of science, because scientifically it was really neat, technologically it was really neat, and you also see historically a confluence between some huge, really enormously expensive money-making propositions coming to a head. And what I'm talking about is the United States and the rest of the world was electrifying at the end of the 1800s. And there was a contest that was honestly a war that was going on between Nikola Tesla and George Westinghouse that you see in this perfect partnership graphic on the upper right here, and Thomas Edison on the other side. Why was it a war? On the one hand, Edison was invested in what was called direct current technology, electrons always moving in the same direction. Tesla and Westinghouse invented and were using AC systems, alternating current power, in their system. Why would that be a war? You couldn't have both in the United States. Edison was there first. He had built power plants every 10 city blocks or so. They burned coal. He generated electricity that was DC electricity. He sent that over wires that he owned through meters that he had designed and owned, and made a lot of money. And he was entrenched in direct current power. Alternating current power technically was a better system. And it turned out the United States ended up choosing correctly, and we standardized on alternating current power. The rest of the world did exactly the same thing in turn, but it wasn't a foregone conclusion that the best technology was going to win. So why is it better? We'll take a quick look at it. The Chicago World's Fair, by the way, was the linchpin in how the contest was won. All the technologies of the day were going to be put on display, and the Chicago World's Fair put this out to bid. They went with the cheapest and the best system, and this gave them a big leg up, Tesla and Westinghouse, when they went to battle for the real prize. What was the real prize? The very first power generating system that the United States did was the Niagara Falls power generating system. And what happened was electrical generation was done there using all Tesla Westinghouse technology, and it locked in the United States as an alternating current place for the rest of history. So the stakes could not have been higher. What you've got here is the Dean Adams generating plant that doesn't look like this anymore, but what you had back in the day was 10 5,000 watt generators that Tesla had designed. They shipped this electricity hundreds of miles to New York City, and it changed everything about how power generation was going to be done. What are the guts of the technology? Check it out. There are two things that are different between AC and DC. The first one in this very simple diagram shows that if I turn a crank attached to a conductor, I generate power out here on these two hoops. And if I tap that power and put it into a wire, the electricity that naturally comes out of it is alternating current, so it takes the shape of a sine wave. The big challenge was that Tesla was the first, and well, he's the first. He wasn't the only eventually, but he was the first and only for a long time guy who developed the technology to make motors that could run on this stuff. Transformers turned out to be the key money-making invention, or money-saving invention, really, that gave AC the leg up. How do they work? You can put alternating current power in on one part of the transformer. That's the primary, it's called. And sort of by magic, we're going to study it. It's cool science. But on the other end, called the secondary part of the transformer, out comes electricity that, depending on how you wind the wires, can be completely different in how it works than this electricity. Here's what I mean. If I send in low voltage here and high current, I can pull out high voltage and low current over here. Why would I want to do that? It has to do with a formula that we've talked about already, and you can see, you can imagine how it might work. The electrical losses in wires follow this formula, I squared times R. So if I want to ship electricity long distances, I want the electrical current to be very small. Well, how can I get the power to be big and the current small? High voltage. That's got to be the way to do it, and transformers make it possible. Okay, so a little bit about the technology in a deeper way. What you've got when you look at this in the lab is voltage is the current, or is the voltage that you measure at any moment. V0 is the maximum voltage of the system. This number right here, omega, is called the angular frequency. And in the United States, we use alternating current power at 60 hertz. Europe operates at 50 hertz, so it's part of why you need a transformer when you go over to Europe. Um, what you should be able to do is to put these numbers together and make an intelligent prediction about what we're going to measure in the lab for the angular frequency when we actually study alternating current electricity. So how does this become practical? Well, let's check it out. In your house, in the basement, there is guaranteed, it's probably gray, but you have a breaker box. It's got single breakers and it's got double breakers inside of it. And to make sense out of those, we can really think about AC power. What I've got actually is two waveforms. I've got a purple or a pink and a blue, and I've laid them on top of each other. And those are called in phase. So if I have two waves that are overlapping with each other, they're called in phase. Here you can see they're slightly separated, slightly out of phase. Well, here's the deal. In our house, we use either this one or this one. So what happens is coming into our house, we have three wires. We have one that's ground. We also have one that's this wave and one that's this wave. Here's the way it works in practical use in your house. All these single breakers are in contact with either the top wave or the bottom wave. And it doesn't matter which one. The AC varies so quickly, 60 hertz, the lights don't care. The vacuum cleaner can use either one just fine. It doesn't make any difference to them. The big upshot that makes this really cool is that when we have a big device, like this one says garage or range, I think actually is what it's saying. An electric range or a thing like an electric dryer uses a lot more power than you can easily deliver through a single system. So what they do is they actually have one of the posts of this breaker on the top wave and the bottom post on the bottom wave. And what you actually end up getting is twice the voltage difference across these two. So if an ordinary wave gives you 120 volts, this one would give you 240 volts, and you can do it all with just those three wires that come into your house. So last math thing, and then we'll give you an easy practical example to take with you. Averaging a sine wave from one standpoint is the easiest thing you could do. The average is 0. The top cancels out the bottom. But that's also senseless when we're talking about AC power, because the electrons in my wall may not be going anywhere really because they're oscillating back and forth, or this way, back and forth. But what they are doing in real life is delivering power. There really is movement of charges. There really is voltage behind them. And so what RMS averaging does is to deal with systems where you have positive and negative values and helps make sense out of them. So how does it work? RMS, you read it actually in reverse order. First, you square all the numbers. So 7 squared becomes 49, but so negative 7 becomes 49. Then you take the mean. So you add up all the values that you've squared and average them. And then finally, you take the square root of all those averages. And what's interesting is you don't get 0, not at all. What happens is the average of the voltage over a whole cycle of a sine wave is 0.707 times the maximum. So if the maximum on this wave was 10, and that was, let's say, the maximum voltage, then the RMS voltage was going to be about, it will be about 70% of that. It's 0.707 or 7.1 volts. So there really is voltage being delivered, there really is current being delivered, and there really is power being delivered. So you want to stop the deck if you want to, write down these formulas for RMS and average, and maximum rather, and use them later. Okay, so here's our practical example. The big thing you need to do in this chapter is just keep RMS, which is average, and maximum separate from each other. The math other than that is really easy. The big thing you need to know is that when we talk about 120 volts for our vacuum cleaner, that was really the RMS. So when we first looked at this problem, we just skipped over the fact that we even had alternating current. And the fact that RMS is an average lets us do that. You can really pretend that you're getting a constant 120 volts, even though it's not true, and it doesn't matter. IRMS, well, when they stamp 10 amps of current on the badge on that vacuum cleaner, that's the RMS, that's the average. And so those are done. Power, we just multiplied RMS current times RMS voltage, and it all works. We get 10 amps times 120 volts, and no problem. We end up getting 1200 watts for the power that a vacuum cleaner is going to draw. That's true on the average. However, there are maximum numbers that are just different numbers. So if you need to go from one to the other, then you can take 120 volts and divide it by 0.707 and get the maximum. And what that turns out to be is 160.7 volts. So literally, the vacuum cleaner that you're using is sometimes seeing 161 volts, and sometimes it's seeing 0 volts. But on the average, it's seeing 120. Same thing is true for current. Sometimes there's more than 10 amps flowing, sometimes there's less. If I take 10 amps and divide it by my 0.707, then what I end up getting is 14.1 amps of current flowing. That's the maximum. And then finally, I can take that RMS and max power formula, where average power is 1/2 of max power, and I can just flip it around. And if I take and pencil in 2 times my 1200 watts, then what I'll end up with is that I get 2400 watts as the maximum power the vacuum cleaner will ever see. So I hope you think that's as cool as I do. It's really interesting, in my opinion. What I'm going to do is just give you one more example if you want to see it. I'm going to leave the slide blank, let you work on it, set it up, and go ahead and do it. So do the work on your own if you want to. Go ahead and check the answers, and we'll see you in class. Bring your questions. Take care, and thanks for watching.